I'm making, these are statements that have been made or that people make. No single weather event can be attributed to climate change. How many have seen this statement before? Climate change is now present in every weather event. Starting to hear that one more. Climate change caused X weather event. Just fill in the blank. As a journalist, I would really like to know which one of these I can say and can't say. And so I'm incredibly excited that we have experts here who are going to help us resolve for all time, in an hour and 30 minutes, precisely what we can say about the relationship between climate and weather. So I won't get it wrong anymore, and nobody else will as well. So that's going to be a great achievement, but we're totally up for it. So that's what we're going to do. And we're going to do it by hearing from Stu Ostro and Jennifer Francis. And let me introduce them. You'll hear from Stu first and then Jennifer. Stu is senior meteorologist at the Weather Channel and the head of the team that keeps track of tornadoes and hurricanes in particular. And I know he's going to tell us about a lot, but including his concern about increasing atmospheric thickness, which he will define better than me, and how that is contributing to weird weather. And then we're going to hear from Jennifer Francis. She's a top climate researcher at Rutgers, and she's been looking at how rapid Arctic changes, which we know are occurring, are reverberating in global weather. Each is going to talk for about 20 minutes, and then we're going to sit over there. I'll ask them a couple questions, and then you guys get to ask them questions. We started a little late. The event's supposed to be an hour and a half long. It might stretch a little bit past 6:30, and then there's going to be a reception outside. So thank you all for coming, and I'll turn it over to Stu. Here you are.
Thank you, Chris. First, a couple procedural notes. One, I had as you can hear, a respiratory thing over the weekend, and I feel fine, but my voice is hanging on by a thread, so pardon my frequent sips of tea. That is just tea. And also, follow up on Chris's remark. And also, I have a lot of stuff to go through and limited amount of time to do it, so I think I'm going to set a new record for the number of slides per minute. Most of it is not heavy content. I can go through quickly, but if there are any questions afterward, maybe we'll have time. So I gotta say, to give this presentation takes balls. What? Why the looks of shock? In fact, I'm gonna take them out and squeeze them for you now, right? Well, it's like Bill Murray said in Caddyshack, no big deal. I mean, I've done it on national television, and the Weather Channel is as family-friendly as you can get. Now, ladies and gentlemen, these are my global warming squishy balls, and by the end of this presentation, you'll know exactly what I'm talking about and the method to the madness. Oh, and by the way, I was introduced as Stu Ostro. Actually, my name is Stu Ostro Ass, and I have documentation on that, which I will show you momentarily. And the title of my presentation is "The Disk Has Degenerated." What in the world could that mean? And so that I can see the next slides here, I'm going to put on my reading glasses. Okay. So I told you I would offer you proof that I have done this on the Weather Channel, and there it is. A bit about me. I'm a meteorologist, not a climate scientist. My livelihood depends on making correct weather forecasts every day. My goal with weather forecasting and climate assessment is to come to objective conclusions, period. Nobody at the Weather Channel, I'll often hear, well, once you were sold to NBC, things changed. No, nobody at the Weather Channel or its parent companies or its advertisers has ever pressured me to change my views on climate change. I am politically independent and have voted for Democrats, Republicans, and Libertarians, so now I've either assuaged everybody or annoyed everybody. But the point is, unbiased conclusion, because I've also been accused, as you'll see, of because I'm a liberal, that's why I'm saying what I'm saying, and I used to be a hardcore global warming skeptic. Speaking of which, Fred Singer, one of the most outspoken and prominent skeptics from back in the day, this is still on his website from something I had written in 1999. Stu Ostro argues that the weather is pretty much the same as it has always been, only that our perceptions have changed. Well, Weather Channel produced a documentary called Hot Planet around that time, and somebody once in the IT department erased my entire email archive, so I'll never be able to retrieve it again. But what I said at the time to my boss was, I thought the Weather Channel didn't feature Fred Singer on the extreme skeptic side enough in the program. But times have changed. I was identified as one of 6 high-profile defectors here. And I don't know whether he's here or not, but it's not just me. It's my friend Dave from college in the 70s. Here's a blog which said, here he, Dave, explains his journey from climate skeptic to one of the leading scientific voices warning about the impacts of a warming world, rising oceans, and acidifying seas. Viewers may wish to compare the similar journey of Weather Channel senior forecaster Stu Ostro. Who's that Dave dude from the 70s? That'd be Rear Admiral David Titley, oceanographer of the Navy, and now Deputy Undersecretary of NOAA, with whom I took classes and I'm friends with. So this was me in 1999. What? Yeah. Nothing to see here, move along. By 2005, this was when I started getting out there, and it was getting hot in more ways than one, and I had this title, It's Time to Wake Up and Smell the Thawing Permafrost. And then 2007, a connection between global warming and weather, which is what I'm going to talk about today, graph of the Arctic sea ice, which has just undergone its stunning decline, and this is at the end of that blog entry. I asked, do we have a problem, Houston? So you go back to where I was there, and now here I am worried. Now let's talk about skepticism. It's a fundamental part of the scientific process and is healthy when in that vein. It is not constructive when it becomes overwhelming and results in being closed-minded. Back up here one. A little bit of a hesitation. So there's a lot of strong terminology thrown around. People who have come to the point of view that I do have been called things such as Warministas in the Twitterosphere. The way I have come to think of it is either convinced or unconvinced is a less inflammatory way of talking about it. And I have become convinced both that of the human role and of the effect that the warming is having on the weather. And what changed? Well, I flew. Back when my parents took me on my first plane trips in the 60s and early 70s, you get above the haze layer, just crystal clear, deep blue sky. Now, took these in recent years not on a stagnant August day, but these were in the middle of the winter, clear, clean air mass, and there's just all this gook in the air. And I know you can't see greenhouse gases, but I thought if you can see all this stuff that you can see, maybe there is something to the CO2 thing. I also became more open-minded to and engaged in the climate science. As a meteorologist, I just either wasn't exposed to it or refused to read the papers or whatever, but one thing led to another. I started to read them. I thought these are from some of the top scientists in the world. I can't refute them. And so again, maybe there's something to this. And last but not least, I started noticing that something ain't right with the weather. As meteorologists, and a lot of my colleagues still are there have been extremes since the beginnings of weather, right? And every day we're observing extremes somewhere, so why should anything be different? But something started to change. And so in addition to those 2 blog entries I mentioned to you, I just became a blogging fool about this. And that led to reactions such as this. And this, I was called a liar, a fascist, a communist. That was 2008. I wasn't even running for president. Insane. Then there was this. I told you I was Mr. Ostro-ass. His charming ability to repeat leftist government talking points while miring in his own idiocy. Apparently Stu Ostro, the snake oil salesman of meteorology. And then there it is, Mr. Ostro-ass. Then the announcement for this seminar on the Yale Forum site. So if a meteorologist is skeptical of AGW, he's ignored, or worse, because he's not a climatologist. But if a meteorologist believes AGW, then it's okay that he's not a climatologist. His opinion still counts. To which I responded, thank you for your comment. I will include it in my presentation. And then it gets better. Yesterday, this. As a result of an article that Mr. Mooney wrote. The response, extreme weather convinced you of man-made global warming claims. Does lightning, by the way, that's misspelled, and hail and crop failure make you a believer in witchcraft as well? Stu, did you even examine any evidence before you made your extreme weather beliefs public? Well, yes, actually, I did. Why do I subject myself to that? Well, I've been obsessed with the weather since I was an infant. So it makes sense that if the weather is changing, I'd be equally obsessed with that. It's my job and my passion to communicate weather information, and the data suggests that something ain't right. This was my first epiphany. These are the what we call upper air charts that we look at. And it was my observation about 2002 or 3 that when I was looking at these, just these lines were in a different place. Just that line over Atlanta, that used to be over Tallahassee more often, and now it's farther north. As if there was some sort of force pushing them north, some sort of warm force. And when I investigated further, the data knocked my socks off. So this is a little washed out there, but you can subtly see reds and blues. This is average departure from average temperatures in the 70s. You can see this, most recent decade. Now this is a lot of blues. This is a lot of yellows and oranges and reds. And what is this? This is what we call 500 millibar heights, which is basically the pressures about middle of the way up in the weather atmosphere. And so you compare the 70s to last decade, on average they've gotten noticeably and significantly higher. It was like, ooh, so it's not my imagination that those lines are getting a little farther north at every opportunity. And think of it like a loaf of bread. I'm not a chef or chemist, and the science isn't the same, but basic idea, you put it in the oven, it rises, the dough rises. Well, same basic thing. And this is a way to visualize it with weather data. The yellows and oranges and reds on the left is the South Pole, the right the North Pole. Surface at the bottom, top of the weather atmosphere and into the stratosphere up top. And those colors indicate that across most of the globe, that those depths, the depth of the atmosphere, the weather atmosphere, and the thickness, the distance between the different layers is increasing. So again, seemed to confirm it wasn't just my imagination. This graph, the red is globally average surface temperatures since the late 40s. The purple is globally averaged 500 millibar heights, in other words, the height of the bread. You can see a very strong correlation. So this is when I went over to the dark side, my second epiphany. This is an email I sent to people at the Weather Channel, December 4th, 2006. The amount of oddities, including not just extremes, seems to continue to increase, and many of them can be directly related to stronger and warmer ridges. 2006 and troughs in response. 2006 reinforces to me something I decided by the end of 2005, which I can no longer accept the mantra of individual weather events can't be connected to global warming, much less be the vocal proponent thereof as I used to be. I know that's sacrilege from the standpoint of what conventional wisdom considers to be sound science, but while one single event does not demonstrate anything, given the context with all the other things going on, if there had been any remaining reasonable doubt in my mind, this severe thunderstorm tornado outbreak has helped to further erase it. Those blue dots are wind damage, red dots tornadoes, and this wasn't July, this was early December. And you can't separate the two. There's always this talk about climate, weather. No, they're just, it's all a continuum, different time scales. A couple of metaphors. If climate is a book, weather is the chapters and pages. If climate is the brain, weather is the heart. Life is a collection of experiences which shape who you are helps shape what that collection of experiences is. My climate was I was the boy from Jersey. Weather Channel had the bright idea in 1995, let's take him, put him out in the plains for 2.5 weeks to chase tornadoes. And I went out there, and it became one of the most memorable experiences of my life. So it was like my weather event is now part of my climate. And also thinking on what happened in the last week to some chasers, it definitely put some perspective on that. So, an email trail a couple years ago, the Ostro hypothesis, as some of them dubbed. This is how it goes, what I blogged about in 2007, and not peer-reviewed yet, but endeavoring to get there with some collaborators. Atmosphere is warming, shouldn't be too controversial. One way that's manifesting itself is by that thickness or depth of layers of the atmosphere increasing by way of the top of the bread rising. It's happening not only in the long-term averages, but also with short-term weather patterns and individual events, which in turn, by ways of ridges and troughs, which Jennifer's going to talk about more, is a key driver for the frequency and nature of recent anomalous weather, temperature and precipitation extremes, topsy-turvy patterns, etc. And here's some very preliminary results, some analyses I and my colleagues have done. So this is the frequency of Stu's squishy ball bulges per year, the strong ridges of high pressure in the northern hemisphere, 1 standard deviation above the mean. You can see actually in the 1950s, which in the inset there is a little bit of a warmer decade, there were more of them than a dip, and then there's it's an erratic trend, but a trend since the 1970s when there's been warming. We break it down by latitude band. This is in the Arctic, the up, down, up, and a big spike in 2005 when it really got my attention, when I started going over the edge. Mid-latitude, same thing, trend up since the 70s. What's interesting here, though, is that in the tropics, seems to be a pretty consistent trend all the way since the 40s. And so that is interesting to me, needs further study. Australia, there have been some incredible weather extremes recently. That trend also shows up very clearly. And again, this is the number of day-to-day really strong ridges of high pressure that in turn affect the weather. My colleague Peter Neely at WSci and TWC, statistics isn't my background, is this correct or not? This is a map of the trend since the mid-70s, oranges and reds, there is an upward trend in them, and again, interestingly, he came to a similar result, or the lower latitudes and tropics showing it most clearly. Dan Huber, C2ES, 3 standard deviation bulges of high pressure. In the tropics, also a pretty clear trend and some spikes recently. Then you compare for 1 standard deviation, his methodology with 3 looks very similar. So there seems to be something going on there. Just a few cases. This is what really got my attention. Got a lot of other people's attention too, the 2005 hurricane season, but for me as a meteorologist, just the fact that there were 28 storms, or there was Katrina, or the Gulf was warm, that's not enough. I need a physical connection weather-wise. And this was it. Here you go. What I'm talking about. I don't even need to get into details of what that is. That's 200 millibars and all that. But it sticks out like a sore thumb, whether you're meteorologists or climate scientists or not. Something was going on there, very unusual, and you can connect it meteorologically to what was happening to the south. Snowmageddon. Pattern look familiar? 2009. Look at the context. Warmest winter on record to the north. So go back to the other slide. The bulging ridge of high pressure consistently to the north, associated with record warmth. The keyword, context. Oh, it's cold somewhere, can't be global warming. Well, look at what's going on around it. More recently, all the cold weather coming down to the U.S., look at what was going on to the north. This is March and April. Very cold in places like the Dakotas, back to Alaska. It was warm in the Arctic, and look at the pattern. Another bulging ridge of high pressure consistently. Sandy. Okay, so it was big and it was this, and again, if there was a connection, what was it? And Jennifer has done the research about Arctic sea ice she's going to talk to you about, and affecting ridges and troughs and all that. These are all the tracks of tropical cyclones, tropical storms and hurricanes over southern New Jersey, going back 150 years. This was Sandy. None in the historical database like it. Look at how strong that blocking ridge of high pressure was. But that could happen at any time, right? It's not part of a signal. Well, look at the trend. This is 50 to 90 north, high latitudes of the height of the top of the bread during October. By far the highest spike on record, and there also is a trend there. So to me, I think we can say, and to Chris's question earlier, it's a matter of semantics. Can you prove that it was caused? No. But what are the odds of that having occurred without the warming? And this week, talk about 500-year flood. The terms are misunderstood, but highest river level going back to 1500. Look at the pattern, the temperature pattern, and it just keeps happening over and over and over again. The tornadoes, we don't have time to get into. I'll just say that more at the scale of a couple miles, no, you can't connect it. But the pattern was like this with the recent tornadoes, and there were precipitation extremes that Chris Burt, weather extremes expert, wrote about. So it's at least eyebrow raising, but inconclusive. But for the tornadoes, but the precip, yes. And speaking of tornadoes, no conclusive evidence that there's increasing intensity or frequency, but these are a whole bunch of cases where they've been unusually far north during the fall and winter. Makes sense. More warmth and moisture getting pulled north, that you would have more tornadoes. Jury is still out on hurricanes, but there have been a lot of extremes and oddities lately. The blue, though, is that there have been very quiet times, and it seems to be part of this weather whiplash, push-pull, back and forth between hot and cold, wet and dry, active, stormy, and quiet. And for some reason, Chris wouldn't let me show all 1,072 slides today, but you can go to tinyurl.com/StuOstro. What began as a hobby, I got a lot of cases, and this doesn't even include this week's one, because I don't have time to do it. And somebody will send a email around the Weather Channel, flooding in Europe. I'll go to the pattern, there it is, another slide to add. So what are the implications for all this? Just have a few slides to go. I think I'm pretty well on time here. For meteorologists and climatologists, be open-minded to looking at the issue in a new way, bridge the two communities, rethink the concept of you can't connect individual weather events to global warming. Now, the extent to which you can do that, we can debate the semantics of, but there are some things happening that are so off the charts and low probability that you got to be able to say something about it. For scientists and policymakers, weather is where climate hits the road. We need to have more of a focus, and that is really starting to happen. Then there's the whole adaptation versus mitigation issue, and this doesn't mean we don't have to wrestle with the difficult issues associated with mitigation, but regardless, we're going to have to adapt. Our vulnerability to natural disasters has increased. Somebody suggested to me, since adaptation isn't like as a word by everybody, maybe resiliency, also preparedness, but it's that theme. We got to deal with it. It isn't just a problem for 50 or 100 years from now, and then what about animals and ecosystems? And it can happen quickly. Several research studies came out a few years ago. It wasn't just hundreds of thousands of years to change the climate. It can change on a dime. And this graph visualizes what's been called the Arctic death spiral. Here's a little more easily digested version. Not only the extent and the thickness, but the volume is just going off the charts. And that is affecting the weather, as Jennifer will get into more detail. Okay, to close, this is a great essay by Richard Somerville, one of the top climate scientists in the world. So what's up with the title of the talk? Well, if you take nothing else away from me today, when they tell you don't bend over with your back, use your legs when you pick up something heavy, do it. Memorial Day weekend, Friday, 2009, I didn't follow that advice. Thought, oh, I've strained muscles in the back. This isn't that. Something ain't right. This is really wrong. Well, ladies and gentlemen, this is my back. This is the L4, L5 disc. That's my spinal column. And it was a ruptured disc, but what really that is showing is it's degenerated. And once it's degenerated, don't come back. And actually, yesterday at the train system in Atlanta, the escalator wasn't working. I carried my luggage, and last night reminded me of that X-ray. Now, if that X-ray had happened, though, if I'd have seen that, I shouldn't have been lifting it that way anyway, but if I'd have known that, I would have been extra careful. But they don't routinely take MRIs for degenerated discs. But at least with me, it's just some pain and mobility. My father in 1996 had a pain in his leg, 4 in the morning, went to the hospital, something with a blood clot, fix it. But then 4 o'clock that afternoon, since he was retired, he was volunteering at the hospital, he knew all the doctors. One of them said, something ain't right. Something ain't right. Makes you wonder about the rest of us that don't know all the doctors, because he was paying extra attention. Next thing you know, he's on a helicopter to another hospital, ruptured aortal aneurysm, 1% survival rate. He was at 1%. And he got 12 more years. My oldest brother, Steve, is part of another 1%. He was one of the top astronomers in the world, worked with Carl Sagan, won the Kuiper Prize, which people like Shoemaker-Levy, Carl Sagan, Van Allen of Van Allen belts, and my brother won. February 2006, he had a pain in the chest. It's a pulled muscle. Didn't do anything with it. That summer, hills above JPL, power walk, shortness of breath. Went to the doctor, x-ray. When a nurse comes back crying, that's usually not a good sign. He had stage 4 male breast cancer, 1%. He was the 1% of breast cancer cases that are male. And put up a courageous fight for 2 years, but didn't make it. If he'd have had that x-ray beforehand, if he'd have gone to the doctor, that first pain, he'd probably still be here. So in each of those cases, my back, my father, my brother, something wasn't right. And I'll end with this graph here. One of the last conversations I had with him, and he was politically conservative, but I said, Steve, because he was like, what's up with this global warming stuff? But he was an objective scientist, one of the best, and I said, the Arctic sea ice, and he knew models, so I could speak about ensembles. These yellow lines here, they ran a climate model, and those were all the individual members. In 2007, which Jennifer's really going to get into here, it was way lower than any ensemble member even showed. And I was like, Steve, I might still be more skeptical if it wasn't for that, but I'm telling you, something ain't right. And he was a scientist, he got it. And so what I would suggest to you as a meteorologist with 30 years of forecasting experience who is skeptical, I'm convinced that something ain't right, and oughtn't we to take those signs seriously? And with that, I thank you.
Great talk, and here's Jennifer.
All right, jump right in.
Clicker over there.
Oh,
Right?
yeah. This is working. All right, well, thank you all for coming. Thank you, Nick. Thank you, Katie. And thank you especially to Rafe Pomerantz, who's here, who I think was sort of the spark that started all this. So I wanted to thank him, too. But it's great to be here. And thank you also to Stu for covering some territory that I won't have to cover. So I've been involved in the last few years, actually just the last year and a half really, on this new topic to me for my research, and that is connecting what's going on in the Arctic, which you've already seen a bit of, and the big changes happening there, and the fact that it's connecting up to the weather pattern changes that we're seeing here in the mid-latitudes. I've been doing this work with my colleague Steve Vavris at the University of Wisconsin. So I want to start by just reviewing a few more of the extreme events that we've seen just in the last couple years around the Northern Hemisphere. And Mother Nature has dished up one heck of a smorgasbord. Just this past winter, this is up near my hometown up in Massachusetts, we were battered by nor'easter after nor'easter this winter. In the UK, they've had a heck of a couple of summers, springs, and winters with a drought 1 minute and then a flood the next. In Alaska last summer, they had the worst flooding in southeast Alaska they've ever had. In Central Europe, as Stu already mentioned, just this past week, they've had some of the worst flooding they've ever had. Last summer in Greenland, you don't usually think of Greenland and flooding in the same thought, but they had the worst flooding they've ever had in Greenland. And of course, the last few winters in Europe have been exceptionally severe, not just in the usual places, but they got snow all the way down to the Black Sea and the north coast of the Mediterranean, or the north coast of Africa, actually, so the south coast, actually. And then in Central Europe, the residents there were very upset by all the snow they got. And then over in Japan, it's just, you can't even imagine the snowplow that they must have used to cut that road. And then, of course, there's been the heat waves. And this picture wouldn't be so unusual, except this was Burlington, Vermont in March, 2 Marches ago. And then, of course, last summer we had some horrific heat waves in our country, which left Texas marinas high and dry, and Eurasia's had their own set of heat waves and droughts to deal with. So the question is, and Stu's already alluded to this, what the heck is going on? And really the question that everybody's really asking is, are we having something to do with this incredible increase in extreme weather that everybody's been noticing now? And you know, it's really only been the last few years where scientists have been able or been willing to step up and answer this question. And now more and more, after we've had a flurry of studies looking into this very linkage, more and more of us are willing to stand up and say, yes, indeed, there is a link between climate change and extreme weather. I like to start by putting this whole situation in context and remind you of the really horrible pickle we've gotten ourselves into. So you've probably seen a graph like this at some point where we're looking at the curve of temperature going back about 430,000 years, the red line, along with the amount of carbon dioxide in the atmosphere, the blue line. And you can see back in time, with time going back to the left, that they worked in pretty close step with each other. And in fact, the temperature oscillations were really due to changes in the Earth's orbit, and the CO2 followed the temperature. But over on the right there, you'll see that something really different's going on. And here's our carbon dioxide levels today. We've recently broken through the 400 parts per million record, which is not a good thing. But what you see is you look at comparing what the carbon dioxide levels are now and what the temperature of the Earth is doing, and you can see they're completely out of whack with each other. We put this carbon dioxide into the atmosphere so fast that the Earth's climate system has not been able to catch up yet. It takes a long time. And it also takes a long time for that carbon dioxide to leave the atmosphere, even if we were able to stop producing it today. So we've got a lot of climate change coming our way, even if we were able to stop producing carbon dioxide and other greenhouse gases. And we also know that the last time CO2 levels were as high as they are now, the globe was several degrees warmer. Now remember, we've only increased the globe's temperature by about 1 degree so far, centigrade. So we've got several more degrees. The sea levels were tens of feet higher, and humans weren't even around then. This was at least probably more like 2.5 million years ago, but at least 800,000 years ago. It's a real pickle. But the Earth's temperature is starting to catch up. And as we look back to the late 1800s, we see that we're on track to increase the globe's temperatures increasing. In fact, 10 of the 11 warmest years on record have occurred since 1998. And what I really want to talk about is the fact that it's not warming everywhere at the same amount. It's warming much faster in the Arctic, as you can see from this plot of temperature anomalies or differences from normal for the last decade or so. And you can see those red colors up in the northern part of the graph are showing that it's warmed much, much faster than the global average up in the Arctic. So this is what we call Arctic amplification. This is another way to look at it, where we can look how temperature has changed in different latitude slices of the Earth. The light blue line is for the Arctic, and you can see that it's varied a lot more than all the other parts of the globe. And you can focus in on the green line too. That's for the northern mid-latitudes. That's where we all live. And so what you see is that the light blue line and the green line have been getting farther and farther apart as the Arctic has warmed much faster than the rest of the globe. The fact that the Arctic's temperature time series has fluctuated so much more shows you how sensitive the Arctic is to the global temperature change. So when the globe was cooler than normal, the Arctic was a lot cooler than normal. So it has a much larger response to global temperature changes. In fact, we know now that the Arctic today is it's warming 2 to 3 times faster than the rest of the northern hemisphere. And this is due to a number of things. It's due to the loss of Arctic sea ice, which you've heard about a little, and we're going to talk about more. It's also caused by the loss of snow in the spring on high latitude land areas. So right now, as a matter of fact, this last month of May has seen the lowest levels of snow cover, especially in Eurasia, but also in the northern North America, than we've ever had. And this has been a very steady trend downward. In fact, the snow has been disappearing in the spring faster than the sea ice has been disappearing, which is saying something. And this is important, especially as we go into summer here, because as we lose that snow on high latitude land, then it exposes the soil underneath it earlier to the strong sunshine, which allows it to warm up, and it gives the continents an earlier start to the heating season. So we're setting ourselves up for a higher likelihood of heat waves and droughts as we lose this snow earlier in the spring. The other factor that's affecting this Arctic amplification is the amount of water vapor is increasing in the atmosphere everywhere, but especially percentage-wise in the Arctic. And the water vapor not only is a greenhouse gas all by itself, but when it condenses into liquid in a cloud, it releases heat into the atmosphere. So that warms the atmosphere, and also we get more clouds forming. And clouds are very good at trapping heat down to the surface. So these are the main factors that are causing the Arctic to warm so fast. Now we can look at this by season too. And this is what I've plotted here, going back to the late 1940s or so. And each of these curves is showing how much warmer the Arctic is compared to the rest of the northern hemisphere. So what you see is that brown curve, which is over to the right there in present times, is showing that the Arctic amplification is largest in the fall. This makes sense because that's when the effects of the sea ice loss are most important. It's also big in the winter. That's mostly because of the water vapor increase, but also the residual effect of the sea ice loss. We're also seeing it starting to happen in the spring. And the spring goes back to that loss of snow that I told you about. And the summer, again, it's both the water vapor and the result of the snow loss. So we're seeing Arctic amplification happen not just in the fall and winter now, but in all seasons. But you'll notice it's a relatively recent signal. It only goes back a couple of decades. And that makes it hard to see how the effects are unfolding in terms of weather changes because it's a relatively short signal. But they're starting to emerge. So let's take a little more look at the sea ice story here. And as you probably know, it's really a mere shadow of its former self. If we look back 30 years, look down on the North Pole, what the sea ice used to look like at the end of the summer when it's at its minimum extent, that pink stuff is all the sea ice, pretty much filling up the whole Arctic Ocean. But if we look at just what it looked like just this past summer, 2012, you can see with your eye that it's just terrifically diminished from what it was only back in 1980. In fact, the amount of sea ice covering the Arctic Ocean is about half of what it was only then. And then if we take into account the thickness of that ice and multiply it by the extent, we get the volume that Stu showed you. And the volume now is about 80% less than it was only 30 years ago. It's just amazing. So, and what's left is very broken, it's slushy, people describe it as very weak, and so it's very vulnerable to any anomalies in the winds or the ocean currents or whatever. And so it's a very different place than it used to be. And we can look back in time actually and ask, how unusual is this? Did this happen before? And we can look at sediment cores in the Arctic Ocean that tell us about how much sea ice there was even back 1,500 years. And you can see this squiggly line. Yes, it varies from year to year somewhat, but it's pretty steady until you look at the blue curve, which is the more modern record, and see how it drops off compared to the previous 1,500 years or so. But then if we put last summer on this plot, you can't. You need a whole new graph. Well, why do we care about the sea ice? Well, as you know, ice is very white, as is snow, and if you have only half as much ice, which is the 2012 is the white, the pink line is what it should be. We have much less ice than we used to have, and so the result is that when the ice is there, it reflects most of the sun's energy right back to outer space, so it never enters the climate system at all. But now, because we have so much less ice, a lot more of the sun's energy is going right into the Arctic Ocean. It's warming it up. And so by the time fall comes along, after all that heat from the sun and going into the ocean, all of that heat then has to be re-released into the atmosphere. This is what it looks like in the fall. So all that heat goes back into the atmosphere in the form of just regular sensible heat, water vapor, and also infrared radiation. And if you calculate how much heat went into the Arctic Ocean just last summer in the areas where there used to be ice, it's about enough energy to power the entire United States for 25 years. Okay, so what's this Arctic amplification stuff all about? Why should we care about the fact that the Arctic is warming so fast? Well, Stu did a great job of introducing this concept. So if we consider a layer of the atmosphere, he showed the 500 millibar surface. We can think of it just of a layer of atmosphere, say extending from Washington, D.C. up to the Arctic. And we know that because it's warmer here, this layer is going to be thicker here in Washington, D.C. than it is up in the Arctic. So basically what that means is that it's forming a hill. It's thicker here than it is up in the north. And so the air wants to flow downhill, just like water wants to flow down the side of a mountain. And as it does so, because the Earth is spinning, instead of going just from the south to the north, it gets turned to the right. And this is what creates what we call the jet stream, which is this fast-moving river of air that basically encircles the northern hemisphere. So what's happening, though, is that because we're warming the Arctic more than we are down here, this hill is becoming less steep. And so the force on that air that's trying to flow northward is not as strong. And so the winds are also weaker. So the jet stream's west to east winds are weaker. So this is a different vision of that thickness of that layer, that 500 millibar layer. And looking down on the North Pole, the blue colors show us that it's thinner there and it gets thicker as you go out to the more southern latitudes. But now look at how the thickness of that layer has changed just in the last, this is just for the last decade or so. So this is actually showing the change in the thickness of that layer. And you can see that those red colors are where that layer has gotten much thicker and it's bullseyed right on top of the Arctic. So this is showing us again how the hill is becoming less steep. And it's this force that drives the winds, the west to east winds of the jet stream. So we can actually measure these winds in the real world and see how they've changed over the last several decades. And that's what's shown here. Going back to the late 1970s, the solid line is the speed of the west to east winds of the jet stream up at the 500 millibar level over time. And what you see is that they start to drop off about 10% slower since about the mid-1990s. And plotted on there in the dashed line is the extent of sea ice, just for comparison. And you see that they both tend to drop off right about at the same time. And we know that when the winds get weaker in the jet stream, with the west to east winds, that the trajectory that the jet stream takes around the northern hemisphere tends to take a wavier path. And you can think of a river flowing down a mountain. When that river is going down a steep mountainside, it tends to go quite directly. But when it gets out to the coastal plain and there's not much slope to the land, you've all seen those rivers that tend to take these big meandering paths. And that's similar to what happens to the jet stream when the winds get weak. So the other effect that we've identified, or first hypothesized, is that if we've got one of these waves in the jet stream, then if you warm the northern tips of these waves, which we call ridges, more than the southern parts, then those ridges should actually get stretched northward. And this is another effect that actually makes these waves larger. So there are two effects as a result of the warming being larger in the Arctic than it is in the areas farther south. But why do we care about these waves in the jet stream? Well, it turns out those waves control our weather. So here's a schematic of a typical jet stream, that orange line there, blowing from basically west to east, but with waves in it. And you can see that it separates the cold air to the north from the warm air to the south. It's the boundary. So if you're south of the jet stream, you're in the warm air. And as one of these waves goes by you, then you might go into the cold air. But the other thing is, these different areas of the waves where the winds are coming from the southwest are where you find the stormy patterns. It's where those storms tend to form as that wind brings the moisture up from the tropics. And then in the northwesterly flow of the waves is where you have dry, settled weather. You have high pressure and nice weather. So these waves have everything to do with the weather that we feel down here on the surface. So this is a very cool schematic that just came out last week. It was produced by John Garrett, and it was put on a wonderful summary of what jet streams are and why we care about them that was on the skepticalscience.org blog. And he produced this nice schematic that shows how when the waves are relatively small, in the upper panel there, they tend to move quite quickly from west to east. But when they get large, like in the lower panel, they tend to shift much more slowly. And why is that important? Well, now you know that there's certain kinds of weather associated with the different parts of those waves. So if you've got the waves that are shallow, then your weather is going to change frequently. But if the waves get big, then you're going to tend to get stuck in the same weather pattern for a much longer time. So now what I'm going to do is show you an actual jet stream from the real world. I've got to jump over here and click on this box. Okay, so this is an animation put together by NASA, and I'm not going to be able to control it for you, but what you're going to see first as we zoom down on the northern hemisphere here is the waves start out quite shallow, and if you look closely, they were moving quickly. But now the waves have gotten much bigger, and you can see that they tend to get stuck. We're forming a block up over Greenland, and there's another cutoff low. I'm going to play it one more time because it goes by so fast. So watch for the shallow waves in the beginning part and see how they move relatively quickly right across the North American continent. So right there, you can see them shifting quite quickly, and then the waves get much larger, and you can see that they tend to get stuck in place, and they even tend to form blocking patterns and cutoff lows, just like Stu talked about. But you can see that real jet stream is quite a messy beast. All right, so that's the theory. So now let's look at some actual analysis that we've been doing to see if this idea is really showing up in the real world. So what we did was we actually looked at how these waves in the jet stream are changing their character. So here's just another way of plotting this thickness of the layer, the height of the layer that Stu showed, this 500 millibar height around the whole northern hemisphere. And what we did was we looked at how these peaks in these waves are changing over time, which is shown in this plot here as the trends in the frequency of these ridges according to longitude. So that plot matches the map up above it. So what you can see is that over on the right there where it's circled shows that the ridges are increasing quite dramatically, especially in the North Atlantic. But you'll see that almost everywhere, almost all longitudes, the numbers are positive. They're all above 0, which means that the trends are positive everywhere, ridges are increasing everywhere. So it matches up very well with what Stu just told you. We can also look at the size of the waves. And remember, we're expecting the waves to get larger. So as we plot how the trend in the size of the waves looks versus longitude, we can see that again, everywhere the values are above 0. And this is for fall only, by the way. So what we see is that the waves seem to be getting larger all across the northern hemisphere, just as we thought they would. We've also come up with a way to measure how wavy the upper level flow is. This is a harder thing to get to figure out, to measure sort of objectively. But we've come up with a relatively simple metric. And basically what it is just looking at how much of the wind is in the north-south direction versus the total wind. And so what this is showing is the trend in the waviness, if you will, of the winds at 500 millibars in the fall. So the blue colors are where it's less wavy, and the red colors are where it's more wavy. And what we find is that there's this big swath of areas starting from North America, across the North Atlantic, over into Europe and Eurasia, where the values are positive. The flow at 500 millibars is, in fact, getting wavier. And the reason it's set up the way this is across the northern hemisphere, if you go back to the changes in the thickness of this layer, it actually makes sense. So over in North America there, you can see that there's that tongue of warming, of extra thick air that extends southward over North America, exactly where we see the waviness increasing. But then it shifts northward as you go around through Europe and Asia, just as the trends in the waviness do too. So it seems to match up with where we're seeing this poleward hill getting shallower. Think back to that hill getting shallower. So we'll take a quick look at summer. And what we see in the summer, again, a very strong increase in the ridges over North America, over North Atlantic, and all the way over into Europe, and also in the North Pacific. So what this suggests is that we're getting a lot more of these ridges in these places, just as Stu showed. And you can think back to his plot of Hurricane Sandy. Okay, almost done. When there was a big ridge in place then, and also we see that there's, the waves are also getting larger, especially in the North Atlantic sector. So just to wrap up quickly, I'm going to look at a couple of particular extreme weather events, and we'll take a look at what the jet stream was doing during those extreme weather conditions. So think back to this past March, where it was quite cold in the east and warm in the west, compared to March of 2012, when we broke thousands of high temperature records during March all across the east. And here's what the jet stream looked like in those two Marches, only 1 year apart. In 2012, we had this big dip over the west, a big ridge over the east that stayed in place for a very long time. That's what, and again, a big amplified flow or big waves in the jet stream. But the next year, big waves in the jet stream, but they're just in a different place. So the same reason, but they're just set up in a different location. And if we look at a couple of other extreme events, those record snows in Alaska that I showed you, look what the jet stream was doing there. You can see Alaska's right up at the top there, with California sort of stretching down to the right, and the gray area is where the actual jet stream was. And what you see is that it's bringing all this moisture up from the central Pacific, but the cold air is over Alaska, and that's exactly the ingredient you need for a lot of snow. But that very amplified, very wavy pattern meant that that pattern was in place for a long time. Spain had some record flooding last September, and once again, Spain is over in the middle of the right side there. You can see the North America on the left, and again, the jet stream was in this very wavy pattern. So just a quick note about Sandy. Stu already covered it, but what we saw in place when Sandy came along, I mean, I'm sounding like a broken record here, but this big dip in the jet stream over the eastern half of the country, big ridge over the North Atlantic, causing that blocking high that brought Sandy right into New Jersey. And what we were seeing in the Arctic at that time, remember this is right after that record loss of snow, of sea ice in 2012, the Arctic was way warmer than normal. So the question is whether that extra warmth in the Arctic had a role in strengthening that block, maybe extending it farther northward or prolonging it. We're not sure, but it could have. And the other factors we need to keep in mind when we talk about Sandy is the oceans were much warmer all along the East Coast. Remember, Sandy came along the end of October, very late to be that far north. But the ocean off the East Coast was warmer than normal. And this is happening right now as well. We still see warm temperatures all along the eastern seaboard. And this may allow hurricane seasons to lengthen. Storms may be able to survive farther north later in the season, where they can interact with big swings in the jet stream like this. So just finally, let's take a quick look at how this particular year of sea ice is unfolding. Starting with the ice extent. Remember, this is the area of ice. So starting in February, and the red dot is today. And what we see is the black line is where it should be, going back to, say, 1980, where I showed you in the beginning. The dashed line is what it did in 2012. And what you can see, the blue line is this year. You can see that most of it, we've been actually below the amount of ice for last year, which blew the record away. So we're already in a bad spot. But then if we look at the sea ice thickness, and here we go from January right through the entire year, each of those lines is for a different year. And if you can see the numbers there, the red line on top is for 1980, and basically you're going through time closer and closer to present until you get to today. And here we are with our ice thickness today. So we're going into this summer with the least amount of ice we've ever had in terms of thickness for this date. So, remember the fiscal cliff? I mean, that was a few months ago, but there it is. And here we've got this other cliff coming our way, which is looking pretty daunting right now. But as Lou mentioned, there is a silver lining to all of this, I think, and that is that this extreme weather that's been affecting a lot of people personally in their wallet, in their families, in their homes, in their food prices, it's got people's attention. The public is starting to listen. The media is certainly starting to listen. Even a few politicians are starting to listen. And I think the good news is this anti-science bunker is really starting to crumble. And I think we have an incredible opportunity here to take advantage of what's a bad situation, but making headway into doing something about it. So thank you very much.
Okay, we're going to move over to the chairs, and I'm going to bring a mic with us. And you guys got to turn on these mics, too. The miking is complicated.
Testing.
We should all be mic'd, are we?
I have a green light. Does that
Yeah,
work?
you're good.
What about me? Looks like I'm live, too.
I have a
Okay.
green light, but it's not. Is it?
Okay, great. So I got a couple questions, and then we'll take questions from the audience as well. These were both really good presentations, really strong. My first question, as a journalist who writes about science, are you guys saying the same thing? And to what extent are you saying the same thing?
Well,
You're saying it in a different way.
But Jennifer's coming at it from a different direction than I am, but what's interesting is that we have converged upon a very similar spot. I, as a day-to-day weather forecaster, Jennifer, who has a background in meteorology, but who is more on a climate science research area, and we're pretty well converged, I think.
Yeah, I mean, we didn't talk to each other before today about
We
what,
just met today.
what we were going to talk about here. And so the fact that we had such a similar message and similar data even, I think is kind of remarkable. And the tropical connection is something new that I haven't looked at, but obviously because I focus on the Arctic all the time, but that's something I think we're going to have to take into account.
So the next question is, this is relatively new, it seems to me. I mean, if I've been reporting on this for 10 years, it seems like it's only a couple years that we've started to hear this kind of interpretation of what's happened. How accepted do you think it is? I mean, Steve is saying that he's working to publish his research. You've published some of it. I mean, are people being convinced by your interpretation of what's happening?
I think most people are. There's a few hardcore atmospheric dynamicists out there who are still not on board totally, but I think there are more and more papers all the time being published using climate models to try to see whether these kinds of behaviors that we're seeing in the real world are able to be captured by these sophisticated climate models. And more, we're seeing studies come out that suggest that the models really are capturing this behavior, especially as they look forward in time to when we have even more carbon dioxide in the atmosphere and even less sea ice and more Arctic warming. And so if we increase the signal, then the response is getting much stronger in the model output. So I think as those studies start to come out, then I think most people are going to, anybody who's not convinced now, I think will be.
Yeah, I think another interesting thing about the way this has evolved is that I was talking about this, blogging about it, et cetera, back starting like 2007. And I did find that I was connecting with, during some of the talks I gave to broadcast meteorologists who have been relatively skeptical, I got positive feedback because I was speaking their language. I was talking 500 millibars and ridges and troughs and stuff like that. But for the general public and also the climate science research community, I think Jennifer publishing through the peer review process this piece of it has opened the door to both the climate science community looking at it more closely, and also it's gotten a fair amount of media attention, so it's all, again, converging.
But one other thing I want to mention is I talked about how this Arctic amplification signal is a relatively new one in the system. And so that's part of the problem of looking at the real world, is that it's really only emerged in the last decade and a half or so. And so it's hard to get good statistics if you only have 15, 20 years of a signal there to measure.
Let me just ask one more question. What does this say about the climate system and the unpredictability of what's going to happen going forward? Again, I'll just say, 2005, I don't think anybody said, oh, that's going to happen. The jet stream is going to get wild, and it's only the last couple of years. I mean, what other things are we not knowing about?
As somebody who had all those and continues to have these accusations and name calling, all just because I've said what I have. There's this skepticism that anything is really going on, and meteorologists in particular, we forecast the weather every day, and if a computer model can't get the forecast right 5 days in advance, how can it get it right? Well, it's apples and oranges. It's two completely different things. But I think what happened with the Arctic sea ice in 2007 shows us is that, yes, models and climate models can be wrong, and they can be wrong in the direction of it happening, changes happening stunningly quickly compared to what any of the models were saying. So it does make you wonder what else is out there. And there's also the question of if the Arctic is warming and there's all these changes going on, what happens? Does it just continue down this road? Or at some point does the whole atmosphere get so warm that it's just one big ridge and we're not getting all these troughs? Or those are some of the sorts of questions with just general theory and modeling to look at moving forward.
But I think in terms of weather predictability, there's good news and bad news. The forecast models are generally not very good at forecasting the formation of blocking situations and the formation of cutoff lows, which tend to be these features that stay in a long time in one place, like Stu showed. But once you get one, then they're around a long time, so your predictability gets really good.
And I just wanted to second that from somebody who, again, makes my living. I got to make the forecast right every day. I have observed, I don't know whether they've quantified this with the predictability of the patterns, but when one of these patterns is coming up, the models are a little slow, and then when that just happened in the last couple of weeks. They're slow, but then once it gets there, it's hard to get rid of it.
And final question, Stu, where can we get the people want the squeezy high pressure balls?
I think it's officeplayground.com
Okay.
for like $1.99 a ball.
They're clicking over right now. We're going to send tweets. So the way we're going to do Q&A, interestingly, is we're going to ask you to line up at the podium where there is a live microphone. Okay, and then so you will actually be mic'd. Identify yourself, and those of you over here, you're just never going to get a question in because they got a huge advantage. I'm sorry, that's. But you might if you move now. And make sure to phrase your question following Jeopardy in the form of a question. Okay? No statements. Do we have any questions? Otherwise, I'm going to have to keep talking to them.
Can I just borrow Jennifer's mic for a second?
I guess, okay, we're going to do this differently than I said. You guys
thank you very much
told
for the
you.
three
No
of
one
you.
would-
Liberals don't follow instructions. Okay, go ahead.
Thank you very much for coming. This has been very enlightening. I've heard Stu's talk
Hey,
a
Joe.
couple of times. And having spent some time on the Arctic ice 50 years ago, it's really a shame to see it going. But I'm curious, between the combination of sea ice loss and the sharp troughs and ridges, in August we had a very powerful winter or summer storm that really stirred up and helped with the ice decrease. And I'm curious if you think there'll be more frequent such storms because of the open water and the troughing in the Arctic.
Yes.
Kind of a feedback.
Yeah, we fully expect there to be more summer storms, and when there are summer storms now up there, they do more damage, because where there used to be ice, and so waves couldn't be generated on the ice, so now it's all open water. We're generating a lot bigger waves. It's causing a lot of erosion along the coast of especially Alaska, and whole villages are looking at having to move because the erosion there has been getting so bad. So, and not only that, but those storms help break up the ice too. So it's sort of another positive feedback in the system. We think that that particular really bad storm last summer probably played a role, but that ice would have been lost anyway because it was so thin. So, yeah. Thanks.
Thank you so much for your interesting and thoughtful presentation. Could you, for the sake of completion, mention what is happening in Antarctica? Your earlier slide showed that the temperature increase in the Arctic region is much greater than the temperature increase in Antarctica. So what leads to this variation? And again, how does climate change over there affects life in the southern hemisphere? Thank you.
I think we're going to make this the question, Mike, because people are afraid of the podium. Go ahead and, well, you probably need it to answer too, won't you?
I do.
Okay. Well, I need a mic to
Unless you don't
pass.
wanna
I need
hear
a mic
it.
to pass. Can you guys share that one?
Sure. Yeah.
Okay. Can I have pass this mic for questions? You guys help me with that? Okay.
All right, so let me take a stab
Sorry
at
about
Antarctica first. So, as you know, the Arctic is an ocean surrounded by land, and the Antarctic is a continent surrounded by ocean. Every year, almost all of the sea ice around Antarctica melts back to the coast. So there's really only one area that has kind of a permanent area of sea ice. And so that effect that I mentioned of losing the ice and then the ocean being able to absorb a whole lot more energy because there's no ice there anymore is a much smaller factor there, because there's just not much ice to lose. The other factor, it turns out, is related to the ozone hole, believe it or not. And as we've lost ozone over Antarctica, it's allowed the upper atmosphere to cool more, because ozone absorbs UV radiation from the sun, which actually warms the layer where it sits. So as we've lost ozone, we've cooled the upper levels of the atmosphere over Antarctica, which is exactly the opposite to what's happening in the Arctic. So instead of decreasing the slope of that hill, it's actually been increasing. And so, in fact, the jet stream down there has been getting stronger. And as that jet stream gets stronger, it has a component of the wind that blows offshore, and so that has been actually blowing whatever sea ice there is there farther away, which has shown up as an increase in the amount of sea ice in the wintertime in the Antarctic. It's complicated, but they're very different places.
Okay, we have a mic that we're passing around the room, so can I see some hands? We've got one back here.
You should offer a financial reward.
Yeah, I don't know. Unruly crowd. All right. Yes.
Thankfully.
Stand up so that the camera can see you. Yeah. Okay.
Hi, I'm Laura Geller with the National Academy of Sciences, and Jennifer serves on our Polar Research Board and has helped bring these issues to our attention. And these are excellent presentations, and you both made a very compelling case for the kind of linkages you're talking about. But Chris raised another very good question about what else do we not know about that's affecting the weather. And I just wanted to ask if either of you are familiar with some even more recent research that's looking at the question of anthropogenic heat pollution coming out of the cities. There was a paper that came out in Nature just earlier this year that's saying this is the big neglected factor in climate models, that we know that all the waste heat coming out of cities affects the cities themselves with urban heat island, but there's evidence that it's having a much bigger, more widespread effect, and you kind of get these heat towers that can actually affect the jet stream and affect atmospheric circulation, and that may be yet another factor that's influencing these dynamics. So I was wondering if you've seen any work on this, if it might have a role.
Gee, thanks. I had seen that paper. I have been asked about it a few times, and I find it very hard to believe that the extra heat coming from cities has any comparison whatsoever to the amount of heat that's being trapped by greenhouse gases. I mean, the numbers are completely overwhelmed, I think. And so, you know, that paper has not really been picked up, and people are not talking about it. In my world, it's not been a very important finding, because I don't think too many people actually believe it.
You want to say something?
No, I've not seen the paper, so. But
That-
what
in
Jennifer
case
just
you're
said
wondering-
makes sense.
In case you're wondering, that is in science, a smackdown. Any other questions? Right here, yes? Can, yeah.
Hi, my name is Shira, and I work at the Environmental Defense Fund. This is for Stu. There's been some polls of public opinion that many people trust their meteorologists with the information on weather and climate and things like that. And what do you see for the prospects of more local weathermen talking about it or believing in this?
So what exactly was it?
Specifically, there's often local weathermen are not talking about climate change when they talk about their weather trends. So how do you see that increasing? Because that does seem to have an effect on public opinion.
The question is, what are the prospects for local TV meteorologists talking more about climate change? And I know Joe has done some work on that. I think it depends on the level of interest of the individual TV meteorologists. It depends on the station. There are a few out there who, like Dan Satterfield, who's a friend of mine, and a few other TV meteorologists who have really focused a lot. I think there's some potential for that to increase, but it is mitigated either by the points of view of the individual TV meteorologists or just the amount of time they have to talk about it and other factors. I'd probably sum it up by saying probably some increase, but limited.
The number from George Mason in 2010 was that almost 2/3 are skeptical of human influence. Does that dovetail with your experience?
Mm-hmm.
But we should add, excuse me, I do have to throw this in.
Oh, you gotta get you got a pillar blocking you from the camera.
Oh, okay.
Come on, come over.
I'm with George Mason, Joe Whitty, and so we've been working on this survey of TV forecasters.
You still got a pillar blocking you.
Just wanna, hi there, camera, where are you? I was on camera for 40 years, so I've had enough of that. But anyway, I want to leave a positive note that, yes, but over 50% of the TV forecasters believe that global warming is happening with a combination of natural and man-made. And so you could quibble about that, but there is 50% of them who believe it is happening. And we're working right now with a Virginia project in trying to increase Virginia TV forecasters. So just that little quick note.
Okay.
Although I would add the contrast between, what is it, 97% of climate scientists, 50% is still a pretty big difference.
It's a big gap.
Yeah.
Other hands, right there.
I'm Mike McCracken. I guess I'm trying to understand why there's been this difference between the climate and the weather people. And it seems to me that each side's been using ensemble simulations, that is running multiple cases to try and get things, but treating them differently. So when, Stu, you run for weather forecasts, you get 10 or 12 simulations now, you even get more from each of several models. And you look at a lot of different cases individually and try and figure out what's happening, and you give possibilities of what can happen. What climate scientists have been doing, because we're thinking of climate, and NOAA uses a 30-year average for climate, is doing long-term averaging and averaging across the ensembles. And so what you see is a very smooth average. And it would seem to me that would be very unusual. I mean, weather meteorologists wouldn't sort of like to see that. It just isn't sort of the way the world works or something. So I guess I'm wondering if what should happen is that the climate simulation should be put out as each of the individual parts of each piece of the ensemble, each simulation, showing that there are differences, that it really does look like the weather, that you do get these kinds of changes, and that maybe then we'd get sort of better communication between the two groups.
We could make them switch jobs.
You have any thoughts on that?
Sure. Yeah, so what was my thought? I lost it. Wait a minute, you say something. I don't remember.
I had one of those moments a few minutes ago, but I got it back.
Oh, yeah, I know.
Clearly, we didn't plan this.
Right, so that's a really kind of appropriate observation to make, especially in the context of the kind of work that we've been doing lately, because we've been looking at, how do the character of these waves in the atmosphere change from day to day. And you can't do that if you smear it out over time and space. Take those two marches that I showed you, for example, where one had the big ridge in the east and the other had the big ridge in the west. If you average those 2 years out, you'll get no signal at all. And so I think the fact that some of the models have saved daily runs, that's what we're going to be using to look at exactly how the jet stream has been changing over time. And you just can't do that even with a monthly average, or certainly not averaging over many ensembles and over time. So it's a different question that you're asking. You still learn things when you look at the average changes, like has the average jet stream migrated poleward, or has it migrated equatorward, or is it drier here on average, or drier there? So there are some questions you can answer that way, but not this one.
Do you want to add anything, Stu?
Well, I might just accentuate what Mike was saying about weather forecasting and ensembles. What he's referring to is we have what we call operational runs of the models, the American GFS model, the European ECMWF model, and it shows a hurricane is going there, a low pressure system is doing this, or the temperature is doing whatever. But then they run ensembles in which the assumption is that humans and science and the models can't perfectly initialize the state of the atmosphere. What goes into the model isn't perfect, so what comes out isn't perfect. And maybe if we got the initial state a little wrong, so let's input a few other different variables right around it, change it a little bit, then what sort of answers do we get? And the idea is that if all the runs of the ensembles are close together, that gives you more confidence. If they're spread out all over the place, there's more uncertainty. If maybe half of them are with the operational and half of them are over there, it's maybe one or the other. But my experience is that sometimes the ensemble output gives a false sense of confidence, like they're all showing one thing when really, but it is a tool that helps us assess the probability, at least to some extent. And I'm visualizing in my mind what some of the ensembles were showing the GFS and the ECMWF with Sandy and the track too.
Let's take maybe one or two more. Okay, we got it.
Thank you, Bob. Sean Strang. What you guys have both been talking about just now makes me wonder whether some of the differences in degree of remaining skepticism stems from different levels of sophistication with the basic statistical analysis. Are there different schools of thought that sort of correspond to different statistical approaches? Just understanding what the numbers mean, given the.
You mean among meteorologists, or you mean? I don't think the public has any statistical approach.
I'm talking about people who have some kind of standing,
okay.
Scientists and/or
okay.
Meteorologists.
Okay.
Well, I think that most climate scientists have a pretty good knowledge of statistics. Meteorologists, like myself, not all of us have a lot of background in that, but my sense and my experience, and I don't know whether Joe's data has gotten into this at all, but it's not statistical skill that's influencing the degree of skepticism. It's other things.
I'd just say that, there are different statistical techniques to be used to answer different kinds of questions. And it kind of goes back to the previous question about, what do you want to know? And so, if you've got the same data and there's a signal there, you should see it, whether you use one way of detecting anomalies versus another way of detecting anomalies. So, if it's a big signal, then you ought to find it. If it's a marginal signal, then maybe not. So.
One more question? Meteorologist.
I am a meteorologist.
Uh-oh.
I'm Tom DiLiberto. I just want Stu to talk a little bit more about the difficulties an on-air broadcaster would have to talk about climate change in 2 minutes or less. And we know nowadays we don't even call them forecasts on TV, we call them future casts. So what would be the difficulties in talking about climate change with all this different nomenclature and trying to get it across to a community that already has difficulties accepting weather?
My answer would be that it's been done and it can be done. I've done it. For the sake of time, I didn't show any video clips, but I'm not on the air regularly, but I've done a number of, they're called packages, like 1.5 to, with sound bites. I've done 1 or 2 segments just on my own, 2-3 minutes, basically explaining everything I just explained without watering it down, boiling it down. I mentioned Dan Satterfield as another TV meteorologist in South Carolina. There are a couple others out there who are doing it. They're biting off pieces of it and producing well-crafted 1, 2, 3 minute pieces to get exactly at what you're doing. So it's not like it's impossible to do it. It's just all these other things that come into play, I think.
Stu mentioned the question a few minutes ago about, somebody says, well, we can't predict the weather a week from now. How can we say what the climate's going to do, 20 years from now? Well, would you believe me if I told you that it was going to be colder in January than it is right now? Would you?
Sure.
Yeah, because the climate system is responding to energy balance changes. The weather is not. Well, it is, but it's in a much shorter dynamic scale. And so that often quiets people pretty quick with that one demonstration.
Especially like Game of Thrones watchers, we're like, winter is coming. So you get to continue this, and you might even get to ask them questions over cookies and other good stuff because there was a reception outside. These were great informative talks, and I want to thank you both.
Thank you.
Signing off to the webcast. Thanks for tuning in.